All right, let's just dive right into it. Today, we're taking what looks like, standard textbook chemistry notes, and we're turning them into a story. A story about two invisible forces that literally run our world behind the scenes. We'll be looking at these amazing handwritten records that detail the quirks, the preparation, and the sheer power of two very different molecules. Welcome to the tale of carbon dioxide and ammonia.
So, here's our roadmap for the explainer today. First, we'll meet our invisible forces. Then, we dive into carbon dioxide, the heavyweight, and check out its real-world uses. After that, we'll meet our pungent lightweight ammonia and explore its everyday uses. Finally, we'll wrap up with the ultimate chemical crossover. Let's get to it.
Section 1. Meet the invisible forces.
Right out of the gate, you can see the total duality of these two characters. Over on the left, we've got carbon dioxide, or CO₂. It's acidic, it's pretty heavy, definitely heavier than air, and it's got a carbon-to-oxygen ratio of exactly 1 to 2. But then, look on the right. You have its chemical opposite, ammonia, or NH₃. This one's basic, it's super light, way lighter than air, and it mixes nitrogen and hydrogen in a 1 to 3 ratio. So essentially, one is this heavy acidic bruiser, and the other is a lightweight basic gas.
Section 2. Carbon dioxide, the heavyweight.
What's genuinely fascinating here is both the history and the sheer scale of this stuff. CO₂ has a molecular weight of 44 atomic mass units, which is pretty hefty. But what's wild is that even though it makes up a tiny, tiny fraction of our atmosphere, we're talking about 0.03% by volume, we've been studying it for centuries. Actually, these notes tell us a scientist named Van Helmont first prepped it way back in 1630 AD. Imagine that. And today, well, we know it's easily produced by heating organic compounds. Basically, everything from the petrol you put in your car to the carbs in your lunchtime sandwich.
Taking a close look at the actual handwritten lab notes, you can see this classic, almost mad scientist setup they use to capture this invisible heavyweight. The diagram shows what's called a Wolf's bottle, and it's hooked up by these delivery tubes right into a gas jar. Notice that long thistle funnel dropping all the way down to the bottom of the bottle? Well, that is exactly where the magic happens. So how do you actually bring this gas to life? Well, you start by dropping some marble chips. That's calcium carbonate right at the bottom of that Wolf's bottle. Then you pour dilute hydrochloric acid down the funnel. They mix, they react, and boom, carbon dioxide bubbles right up into the gas jar. But, and this is a big but, you have to be careful. Missing just one little detail ruins the whole thing. The notes put a huge warning on avoiding dilute sulfuric acid. Why? Because it actually creates this tough, insoluble crust of calcium sulfate right over the marble chips. It literally chokes off the entire reaction after just a few minutes.
Now, if you ever need to prove this gas is actually in the room, chemistry gives us some really cool visual tricks. Because CO₂ is slightly acidic, if you drop a piece of moist blue litmus paper into a jar of it, it instantly turns red. But it gets better. If you pass the gas through perfectly clear lime water, the water turns cloudy, like milky white. Oh, and the notes mention a fun little extra detail. If you just keep pumping the gas in for a long time, that milky color magically vanishes because it forms a new soluble compound. It's like a magic trick.
Section 3. Real-world uses of CO₂.
This gas is absolutely everywhere, and it is incredibly versatile. When you dissolve it in water under pressure, that's what gives you the fizz in soda water, your beer and Coca-Cola. Take it the other direction and freeze it down to a freezing -78°C, and you get dry ice, which is an absolute game changer for keeping things like vaccines cold during transport. Oh, and bakeries. Yeast literally feeds on sugars and burps out CO₂, making those little pockets of gas that turn flat dough into fluffy bread. Plus, because it's so heavy and snuffs out flames, it's exactly what's inside standard fire extinguishers. It just blankets the fire and starves it of oxygen.
But here's a totally beautiful contradiction. It's kind of mind-blowing that a gas we literally use to violently choke the oxygen out of a fire is also used to save lives. There's this specialized medical cocktail called carbogen. It's a mix containing 10 to 15% oxygen, with the rest being carbon dioxide. And medical professionals actually use it in artificial respiration to help pneumonia patients breathe. Talk about a double life, right?
Moving on to Section 4. Ammonia, the pungent lightweight.
All right, let's flip the script and meet our second character. This incredibly light, frankly tear-inducing gas. Ammonia has a molecular weight of just 17 atomic mass units. That's way less than half the weight of CO₂. Discovered by the legendary chemist Lavoisier, it's a basic, colorless gas, but man, does it pack a punch. It has an intensely pungent smell that will literally bring tears to your eyes. And get this, while we only have tiny amounts of it floating around our atmosphere or dissolved in our soil here on Earth, it is found in massive swirling clouds on the gas giants of our solar system: Jupiter, Saturn, Uranus, and Neptune. Extraterrestrial gas, anyone?
Looking at the lab notes again, you immediately see this isn't the cold liquid mix we used for carbon dioxide. No, this authentic lab diagram shows extracting ammonia takes a much more intense setup. You've got a Bunsen burner blasting heat onto a slanted, downward-facing hard glass test tube, which then forces the gas through this specialized drying tower filled with lime.
The precision you need here is absolutely crucial. To make ammonia, you have to mix ammonium chloride and calcium hydroxide in a very specific 2-to-1 ratio before you start heating it. Now, because ammonia is so much lighter than air, you actually collect it by forcing the heavier air downwards. But here's the catch, the most important step. You have to pass the gas through that lime tower to dry it out. You see, ammonia dissolves so intensely in water that you can't just collect it over water like normal gases. And the notes specifically warn you off using standard lab drying agents because they'll literally start a whole new chemical reaction with the gas. You have to use the lime.
Okay, but what if you want to make a massive amount of it? Like for industrial use? Well, you can throw the little glass test tubes out the window. To make ammonia on a global scale, you need a staggering 500 degrees Celsius and up to 900 atmospheres of pressure just to physically force the nitrogen and hydrogen atoms to bond. It is extreme chemistry. Now, if the eye-watering, tear-inducing stench wasn't enough of a clue that you've got ammonia, chemistry offers another really dramatic visual test. If you take a plain glass rod, dip it into some concentrated hydrochloric acid, and just hold it near the gas, bam, it instantly produces these thick, dense, white fumes of ammonium chloride. That smoke is the absolute, surefire, undeniable proof that ammonia is in the room.
Section 5. Real-world uses of ammonia.
The duality of this molecule is just as astounding as CO2. On one hand, ammonia is basically the backbone of global agriculture. It's manufactured into massive quantities of chemical fertilizers, like ammonium sulfate, which literally helps grow the food we eat. Also, in its liquid form, it evaporates so fast that it makes a fantastic cooling agent for giant industrial refrigerators. And because it's a strong base, it's used as a hardcore cleansing agent to aggressively strip away heavy kitchen grease and oils. But here's the dark side. That exact same irritating property that melts through kitchen grease, that's what makes it a potent ingredient in tear gas, weaponized to control massive crowds. Talk about a double-edged sword.
And finally, Section 6. The ultimate chemical crossover. This brings us right to the climax of our explainer today. What happens when the heavyweight meets the lightweight? Well, you don't get a huge explosion. You get a miracle. You get urea, which we have represented here by its chemical structure. This right here is a vital chemical fertilizer that quite literally feeds the modern world.
Just look at this incredible chemical equation from the notes. Under immense pressure and blistering 1500 degrees Celsius heat, one molecule of carbon dioxide reacts with 2 molecules of ammonia to form urea and water. Think about that for a second. By taking an acidic gas that we use to put out fires and smashing it together with a basic tear-inducing gas under extreme heat, human beings figured out how to create the very chemical foundation of modern agriculture. It's like a giant puzzle coming together.
So what does this all mean for you? How do these invisible, sometimes outright poisonous gases directly impact your life? Well, by diving into these meticulous lab notes, we see that chemistry isn't just dry formulas scribbled on a piece of paper. It's the hidden machinery running our daily lives. These completely invisible, sometimes noxious, and seemingly abstract gases are actively shaping the world you interact with every single day.
Seriously, think about it. From the refreshing fizz in that afternoon soda you might be drinking, to the bread on your sandwich, all the way to the incredibly complex nitrogen fertilizers that literally grew the vegetables on your plate. Which of these invisible gases is shaping your day right now? I'm going to leave you with that thought. I really hope this explainer has sparked your curiosity to look just a little closer at the invisible world around us and to appreciate the magnificent chemical balancing